接下来，我们非常荣幸邀请到 NVIDIA 解决方案工程架构副总裁 Mr. Mark Hamilton， 以及 NVIDIA GPU 深度学习软体开发总监 Jonathan Cohen 来为我们带来今天第一个主题演讲：深度学习与 NVIDIA GPU。Now let's welcome Mr. Mark Hamilton.
你好. Now, hopefully you don't expect me to say any more in Taiwanese. So the GPU Technology Conference is a very special conference. It's very different than any other vendor has. This isn't so much about NVIDIA telling you about our products. This is about all of the nearly 500 employees of NVIDIA in Taiwan celebrating with you your achievements over the last year. And it's been a rather amazing year. Taiwan, of course, is a country we are very thankful for because over 80 to 90% of the GPUs that we ship are shipped in servers that are designed and manufactured right here in Taiwan. And there's a very big shift going on in the industry and many changes from a year ago. Even 1 year ago, we would have spoke about GPUs and their power, about GPUs in a server. And today we really talk about the GPU accelerated data center. Because whether it's new GPUs in Amazon Web Services, in Alibaba, that recently introduced GPUs as a service, IBM's SoftLayer Cloud, or all of the large consumer web companies, including companies like WeChat, which you'll hear from today. And I know there's many WeChat users out there because I turned on my phone earlier and looked at nearby, and there were many within 100 yards, and that was before people walked in. So welcome to GTC in Taiwan, and while it's not quite as beautiful as in the picture today, it did stop raining for all of you to come to the show. So here's a little bit of what we've been working on over the last year. High-performance computing, deep learning, PC virtualization, cloud gaming. Are there any gamers out there? A few. And one thing that we haven't talked for a while, but is rendering. As buildings like anything from Taipei 101, tremendous works of engineering, to small consumer devices, more and more digital design is important. So we'll talk about some of the advances in the last year in all of these areas. In high-performance computing, it's amazing the problems that are continued to be addressed and the new developments. This particular picture up here is of a special type of cancer that about half of you in the room don't have to worry about getting, but all of us know someone that could potentially get it. It's actually ovarian cancer. And ovarian cancer is a very deadly disease. It impacts and kills tens of thousands of women a year. And until this year, there was no vaccine for it. And this year, for the first time, a group of researchers in Notre Dame University in the US and the University of Connecticut developed an individual vaccine for ovarian cancer. And today, if it's detected early enough, using NVIDIA GPUs will sequence an individual's genome and produce a specific vaccine for you as an individual to help cure ovarian cancer. Just one of the many things that GPUs are helping to solve today. Now, of course, 20 years ago, 15 years ago, 10 years ago, about the only thing we talked about was gaming and rendering using GPUs in design in your HP or Dell or Acer or Supermicro workstation. And today, for the first time, using our latest Maxwell family of GPUs, at SIGGRAPH, the world's largest computer graphics show, held just last month in Los Angeles, California, we announced our new NVIDIA DesignWorks software. I'm not going to go through and talk a lot about the details of it, but what DesignWorks does is let you, for the first time, in real time on your workstation, do physically based rendering. And physically based rendering, if you're not a designer, is maybe a little bit of a funny word. But when a designer works on a CAD model, you probably have all seen wireframe models. Of course, a wireframe gives you an idea of the shape and size of the product, but not really how it's going to look. So designers have historically used an NVIDIA GPU, and they've provide colored surfaces. This is in the US, designers call this clown colors, because it looks a little bit like a clown, and it doesn't look like a drill. So why have they done that? Well, because with a single GPU, was not powerful enough to make the drill look like a real-life drill. That so-called rendering or photorealistic rendering took time to do. So the designer would do a design like this with clown colors, go home for the day, and let a large server farm go in and render what looked real. And now with our Maxwell GPUs in DesignWorks, you can actually, in real time, while you're working your design, have a photorealistic rendering. So I doubt any of you in this room can tell which one is a photograph and which one is actually rendered in real time by a GPU. And I won't actually test you because it doesn't matter, but think about it. Instead of, if you're the CAD engineer and you're showing the designer, well, do you want your drill to look like this? And come back tomorrow and I'll show you what it really looks like. Or to say, do you want it to look like this? And then you say, well, maybe I don't like that yellow plastic. I'd like to have it orange or a different color. You can do that in real time. Now, designing a drill is interesting. And in fact, there's many different things that people design all the time. An average cell phone has 10 to 15 different types of physical materials: plastic, metal, glass, the frame in it. But designers, of course, build things that are much, much bigger. I tried to find a building in Taiwan that Gensler designed. Gensler is a world-leading architectural firm. As it turns out, they don't actually have an office in Taiwan. And it's maybe not the best example because the building that Gensler is most famous for building is actually the building that replaced the Taipei 101 Tower. The Shanghai Tower is the world's largest building. But hopefully you don't hold that against the company that is designing NVIDIA's new headquarters. Now, of course, NVIDIA is headquartered in Silicon Valley. So when we started to design our building, our CEO, Jensen Huang, who's Taiwanese, in case anyone didn't know, he wanted a very special building. He wanted a building that reflected the values of the company. He wanted a building that reflected Silicon Valley and the way people work. And more importantly, he wanted a building that showcased our technologies. So instead of building a tall building, or even a 5- or 6-story building, as many companies build in Silicon Valley, we built just a 2-story building. We built that building to bring together up to 2,500 NVIDIA workers in one building. There's very large expanse of glass, 200 meters on one side of glass when the building is complete in 2017. Now, of course, building this and designing this, it's all designed in CAD models before. But we wanted to do something very special. Right? We wanted to not just be able to look at the drill or look at a desk inside the building. We wanted to be able to walk through the whole building. So we actually used 120 GPUs running in the cloud, working together to do physically based rendering of the design. And I can't show it to you today because Gensler is still finalizing the interior design. They're deciding what color the carpet should be, what color the paint should be on the walls. And every day, they go in and they show this to Jensen and to our designers. So we're very happy about the building. We actually broke ground on the building. Of course, since drones are very easily available, we're taking daily drone shots and collecting lots of big data ourselves. And so on July 2nd, before construction started, you can see the 5 buildings at the bottom that this is replacing. And as of last Friday, last time, you can see the 5 buildings are gone. If you look carefully, and let's see, the bottom left, you can see the foundation that is starting to be poured. But of course, since we can do some GPU-based enhancement of the image, we'll show you a surface model. And here you can very clearly see the start of the foundation. So again, we welcome you to hopefully in the next several years you get a chance to visit our headquarters in California, and we can show you then the real versus rendered model. So designer workstations are great when you're doing very complicated designs. But the fact is that today, every device that you use already has a GPU of some type. Your PC, your notebook, your smartphone, your tablet. Now, of course, these don't all have NVIDIA GPUs in them, but they have a GPU that's good enough and gives you much better graphical performance, real-life interaction. Even looking at videos and graphics, 3D graphics on your cell phone is possible. And that's great for a consumer device. And the challenge has been in the data center, in the enterprise data center, that as you wanted to move PCs into the data center and virtualize them, you really couldn't do that with any level of graphical performance. So VDI, or virtual desktop infrastructure, has primarily been used for so-called task workers, right? Someone at the bank, someone at a call center that had a very simple screen. Because the problem is, while your cell phone or $200 tablet has a GPU, a powerful GPU in it, when you buy a $3,000 CPU for a server and put it in a server, a VDI server that's $10,000 or $20,000, there's no GPU in that server. So starting several years ago, we started working on a technology called NVIDIA Grid. And increasingly, as our consumer devices become more and more graphically rich in what you use every day as a consumer, when you go back to the office and your boss tells you that they're going to implement VDI, you still want that same level of graphical performance. So last year, we actually teamed with Citrix and VMware to deliver for the first time GPU-accelerated graphics in the cloud. And actually just today, or just Monday, in Santa Clara, at the VMworld conference, we announced Grid 2.0. So it's very simple. We say Grid, it's our second version of Grid. It's twice as powerful, the GPU. It can serve twice as many users on the same GPU that's shared. There's twice the number of operating systems, because now, besides supporting Windows, we support Linux in a virtualized environment. So again, we're very happy with our developments in Grid. And if you read anything about VMworld this week, I'm sure you'll see a lot about Grid 2.0. So shifting back to HPC. This is really 10 years ago where we started our investment in CUDA, or programming language for the GPUs. And this is what has set, over the last decade, NVIDIA apart, really, from other different types of accelerators. And that we've had a robust ecosystem of partners. It's not just about the NVIDIA GPU. It's not just about the CUDA programming language. It's about the hundreds of different applications developed by hundreds of partners, taught at thousands of universities, and downloaded millions of times to run on literally hundreds of millions of GPUs. Because nearly every GPU that we've shipped in the last 10 years is able to run CUDA. Now, of course, some of those GPUs are more powerful than others. And in the US, which lagged a little bit behind, I'll say, as a US citizen in high-performance computing, we're very proud last year that the US Department of Energy announced a program called Coral. And 2 of the 3 supercomputers that were announced to be built under Coral are based on NVIDIA technology from our partner IBM. And IBM's here at the show, and we'll be talking today. These systems will be deployed at the end of 2017 and will be among the most powerful in the world. Now, following on to the Coral announcement, just several weeks ago, President Obama in the US announced a new National Strategic Computing Initiative. Over $500 million of funding will go into this program for supercomputing just in 2016, with more following on. And the goal is to build supercomputers that are 30 times more powerful than exist today. And if you think about it, the types of problems that remain to be solved. I talked about how GPUs created a vaccine for ovarian cancer. There are still many, many different types of cancer that we can't cure today. Think about global climate change, change in the weather, predicting the weather. Still a very, very tough problem that can't be solved. And it can't simply be solved by Moore's law. And in fact, in the initiative, President Obama called for a path forward in the post-Moore's law era. So even the US president, that is sometimes, depending on your politics, our presidents are criticized more or less, but even the US president concedes that you need accelerated computing technology to move forward. So we're very excited that NVIDIA is a core part of this initiative. But moving to Asia, again, what are some of the large supercomputer centers and supercomputing nations in Asia doing? Certainly Japan, over the last many decades, has been a leader in supercomputing. And one of my good friends, Professor Satoshi from Tokyo Tech University, they're building now their 3rd generation of GPU-accelerated supercomputers. And I think he summed it up very well when he said their next system will not only be about high-performance computing, but it'll be about big data and cloud computing workloads. And he, of course, is not just very well known in Japan. He was actually chair, or is chair, of next year's International Supercomputer Conference. It'll be held in Europe. So again, this is very consistent with our theme of the GPU-accelerated data center. We see GPUs being used not just in high-performance computing, but in all sorts of big data workloads. And increasingly, the data centers that people build, the HPC data centers, the big public cloud data centers, the big consumer web companies building out large internet data centers, will have a platform based on GPU computing. So I'm not going to talk about any new GPUs. I'm actually not going to talk about any specific GPUs at all. But I will talk about one new technology that we introduced earlier this year at our GTC in the United States. And we're very excited that this will start shipping, is planned to start shipping next year. It's called NVLink. And one of the things that we realized from our customers, all of you, several years ago, is that customers, once they started using GPUs in their server, they wanted more of them. And not only did they want more servers with GPUs in them, but they wanted more GPUs in the server. They said, could I have 2 GPUs? Could I have 4 GPUs? Could I have 8 GPUs? And the more GPUs you have, the GPUs, of course, deliver more power. But those GPUs need to communicate. And the server infrastructure today of a standard server just wasn't built for providing that performance. In fact, today, many different types of algorithms, after you get to 4 GPUs, it's hard to scale above. And you have many very smart PhD programmers at universities and at companies working to scale beyond 4 to get to 8. So we realized that we needed to innovate not just in the GPU, but in the connection between the GPUs. And this is what NVLink does. So again, you can see some of the performance benefits that you'll get with NVLink starting next year. Again, up to twice the performance with the same GPUs simply by connecting them with NVLink. And in some of the breakouts today, you'll hear more about NVLink. You'll hear from IBM, how they're implementing NVLink not only between GPUs, but in their Power 8 and 9 CPUs. So again, all of the major data center OEMs are working with us to support NVLink. Because again, NVLink is not only in the GPU, but it's in the server, letting you connect the GPUs. And I'm very excited to say, since I'm here in Taiwan, that the leading OEMs, right, are not the traditional large US-based OEMs. There's companies like QCT, Taiwan, and others that are right here in Taiwan. There will be some of the first in the world, or the first in the world, to announce support for and ship NVLink-based GPUs next year. So again, drawing the picture of what we believe a data center looks like today and increasingly will look like in the future. So you'll have servers that are all GPU accelerated, all have GPUs, and as a user, as a software developer or user of applications, it doesn't matter whether you're running a rendering application, you're doing PC virtualization, you're doing high-performance computing, or doing deep learning, you can run on the same GPUs in the same server in the same data center. Now, in the deep learning space, we've had a tremendous number of advancements over the last year. And so rather than try to speak to those myself, I'd like to invite up our Senior Director of Deep Learning Software, Jonathan Cohen. He has to get his talk done on time so he can go back to the US and get back to work with his team developing the deep learning software. But Jonathan, here you go.
Thank you. Hi, good morning. Welcome to GTC. There we go. So I wanted to, rather than just dive in and talk about, I don't know, all the interesting things people are doing, I wanted to actually explain what is deep learning. It's a term I think everybody has heard of by now. It's in the press. It's in certainly anything from NVIDIA. Any communications you've received from NVIDIA have probably mentioned deep learning. People who are building servers are hearing about it from their customers. But I thought it would actually be helpful to explain a little bit what is deep learning, go beyond the buzzword and describe the technology a little bit for everybody. So deep learning is a term that refers to a set of techniques for teaching a computer a concept. And generally it refers to what's called a neural network. And what I mean by a neural network is actually a very old algorithm. It's been around, I think, since the 50s originally, but let's say 30 or 40 years in the present form. So very old technology that's loosely based on how the human brain or how biological brains are organized, very loosely. And the idea of a neural network is that you create a sequence of transformations. So you have an input that comes in on one side. So in this case, we have an image, and an output that comes out the other side. In this case, the name of the kind of car. And in between, we have several very simple transformations. And I'll explain what these transformations are in a moment. But the idea is that by layering many transformations together, we can create a system that's capable of computing very complicated concepts. And when people talk about a deep neural network or deep learning, they're simply referring to, rather than a few layers of transformations, having many, many layers deeply stacked. And so the idea is that each one of these layers is going to take its input and transform it into an intermediate output that's a little bit more abstract. And as you progress through this deep neural network, you map from something that's very tangible, like pixel values in the image, into a more abstract representation where the computer is able to reason about the content of that image, for example. Or if the input is an audio signal, it can reason about the content of the audio signal, and so on. So for example, in this case, we would start with an image, which is just a list of colors, right? For every pixel in the image, we have the color. That's not abstract at all. That's, in fact, a very difficult representation to work with. And what the first layer is going to do is visualized in the second panel from the left, is actually going to look for edges. So what you can see here are a set of what's called filters. This would be in what's called a convolutional neural network. And each one of these filters is a little oriented edge. Right? One is going to look for edges like this, one is going to look for edges like that, one will look for edges like that. There's one that's going to look for a light corner, one that's going to look for a dark corner. And those filters are going to run over the entire image. And the output of this layer, rather than an image, is basically going to be a line drawing. It's going to be, where did I find all of these kinds of edges? And a line drawing is a slightly more abstract representation than the original image. The next layer might do something like is visualized in the third panel here. So let's say it's looking for one of these little features that looks like a hood. And let's say a hood is made up of a collection of edges. So we can take the output of the previous layer, which is going to be, where did I see all these kinds of edges? And now we're going to look for little tiny patterns, an edge like this, an edge like this, a corner like this, and another edge. And that's going to represent a shape that might be part of a car. So this would be a wheel, or this would be a little fragment of a car window, or this would be a bumper. And again, we've transformed it from now this simple line drawing into a representation that's going to say, well, there's a bumper here, there's a window here, there's a hood here. And then finally, a car that we might recognize would be a collection of these kinds of shapes. It would have two wheels and a bumper, or maybe it has a hood and next to a bumper, next to a wheel, next to some other part of the car. And so you can see as we go through this neural network, as we go to deeper and deeper layers, we're building up in what's called a hierarchical way the concept of a car from these simpler representations. And so that's what people mean when they talk about a deep neural network or deep learning. Does it work? There you go. So that's what a deep neural network is, but what does it mean to learn? So the reason why this is such a powerful technology is that we can actually teach the computer to recognize things like types of cars or types of images or audio signals, converting an audio signal into a speech. And we do this by teaching the network, by showing it many examples. So typically you would have some kind of software that would implement a learning algorithm. And you do the following. So you initialize this neural network. Rather than looking for edges or looking for specific shapes, initially the neural network is completely random. all of those filters, all of those things that it's looking for, it starts out totally random. And we start out by showing it an image. So I'll show it an image of a dog. I'm going to run the neural network, what's called forward propagation. And because it's random, it has no idea, it's going to just randomly say, oh, that's a turtle. Well, it's not a turtle. We know it's a dog. So what we're actually going to do is compute a change to all of the weights, all of the parameters that describe this neural network, and push it a little bit in the direction that makes it a little bit more likely to say dog and less likely to say turtle. So we're just taking this network that starts out random, and we're just going to make it a tiny bit better. And we propagate those changes through the neural network, what's called backpropagation. And then we repeat with a new image. So now I show it a cat, now I'll show it a tree, and I'm going to do this many, many times. And when I say many times, I mean 100 million times. Huge amount of computation involved, right? Because every time we show it one image, we're just going to make it a little bit smarter. And to teach a neural network something as complicated as recognizing an image, or recognizing human speech, or reading a sentence written in some human language, you're going to need a huge amount of examples and a huge amount of learning, right? But once we've done this learning, so this might take several days or several weeks even. Once we've done this learning, we've what's called trained our neural network, and now we can save that model. We never need to do that again. Now I can load that model back in some other device, so I can run this in a cloud, in an embedded device, on my cell phone, in a car. And now I can show it a new image. So this is a picture of my cat, Hagrid. And the network will look at this image, and hopefully, even though it's never seen this cat, it's never seen this image, it has learned the concept, and it will say, ah, this is a cat. So this is the idea with deep learning. This first part, where we're teaching the neural network by showing it many, many examples, is what's called training. And this second part, where we're taking the trained model and using it by showing it a new data, is called inference. And typically, training is something you're going to do on very large, very expensive servers, and inference is something you might do in a more lightweight environment. So I want to talk about one really interesting example, what I think is an incredible application of deep learning. And this is a project, it's actually an old project called Project DAVE. DAVE stands for DARPA Autonomous Vehicle. DARPA is a US agency that sponsors research in very advanced areas. And they typically do this through contests. So for the last maybe 10 years, they sponsored a series of contests and competition and research programs in autonomous driving. So DAVE was one of the entrants in one of these programs. So the idea behind DAVE is that in order to teach a computer to drive, in this case it's a simple robot, not an entire car, but it's the same idea, we're actually going to have it just watch a human driver. So the training set for DAVE is going to be input images from a camera. And what DAVE is going to learn, remember, a neural network just maps from an input to an output. So in this case, this neural network has 3 outputs. Go straight, turn left, turn right. That's all it needs to know. And I'm going to teach it what to do when I see an image. So here's an image of a playground, and the human driver sees this image and says, I need to turn to the right so I don't hit it. Here's an image of a lawn covered with leaves, but we can keep going straight. There's nothing in front of us. And here's an image where there's a tree. And again, to avoid the tree, the human driver will turn left. And so DAVE was trained using a deep neural network to learn these basic operations. From this input image, what do I do? Left, straight, or right? That's it. And the idea behind DAVE is very similar to what's shown in this video. So this is a video of a baby playing ping pong. I could watch this for 10 minutes. It's amazing. And what's happening here, so ask yourself, how is this baby able to hit that ball? He's probably not doing some kind of complicated structure for motion, stereo reconstruction. He's not tracking the ball using a feature tracker. He's not computing path plan. He's not computing inverse kinematics. What's the optimal joint angle? Right? None of that's happening. This baby has simply learned when I see the ball, I do this. Right? From visual input to an output. And so this is the idea with Dave. We're going to teach a robot to navigate by simply learning from a visual input to a control output. So this is Dave. So Dave was done about 12 years ago, or 11 years ago. It was run by Jan LeCun, a very famous pioneer in deep learning, and Urs Müller, who's now the head of autonomous vehicle research at NVIDIA. And so Urs reconstructed Dave, pulled it out of the closet, and put it in his backyard. So this is Dave running in a backyard it's never seen before. And what you can see it's doing is it's never seen those tiles, it's never seen that garbage can, it's never seen any of these obstacles. Let's see if I can replay Dave. And it's able to successfully navigate through this environment. Try one more time. There we go. Even though it's never seen any of it before, with a very, very simple brain. The neural network that's driving Dave is actually tiny. And the computer that's running inside Dave was a computer from 2004, so very slow by today's standards. And it's able to avoid the pole, it's able to avoid the garbage, it's able to know that it can drive on the grass, it can drive on the tile, but it can't drive through the fence. I mean, really amazing bit of intelligence for such a simple robot. And so in order to advance the state of the art in autonomous vehicles, NVIDIA has introduced a platform called Drive PX. So Drive PX is based on our Tegra processor, which runs exactly the same CUDA platform, the same deep learning software as our servers. Everything NVIDIA does, we run the same software platform from our smallest up to our largest. One of the things that makes Drive PX a really interesting platform is it supports up to 12 cameras as input. So if you think of a car that would maybe navigate through traffic using a neural network or other technology similar to Dave, it's going to need many cameras around so it can sense and it can see what's happening. And then Drive PX includes all of the software that we've developed for deep learning, all of the software our partners have developed. And it's an easy platform for prototyping, right? It just runs CUDA, it runs Linux, it can run the different embedded operating systems used in the automotive industry. So this is an example of one of our partners, a company called DesignWorks, running this software. So they write software for autonomous vehicles. And this is showing live what's happening in the car. You can see the blue dots is where it's detecting the traffic lanes. The red vehicles are vehicles it's tracking that you might be concerned about hitting. And green vehicles are vehicles that are far enough away that we're less concerned. And you can see at the top, it's actually reconstructed, just from this view, an overhead view of the highway, where we can see the different lanes. And the green is marking where it believes it's safe for the car to travel, and red is where it would not be safe. So all of this is happening running on this Drive PX. And they ported their software in just 3 weeks because, like I said, it's a very easy platform to develop for. So that's one use of deep learning. Oh, sorry. This is what the platform actually looks like. It's a pretty small module designed to fit in a car, obviously. That's one use of deep learning. Actually, the next keynote after mine, you're going to hear a whole bunch of really amazing uses of deep learning. Basically, every major company in the world today is investigating this technology seriously. I think it's going to have impact from not just the internet search companies, but all areas of our technology sector. Manufacturing, building inspection, healthcare, I think they're all going to be impacted. So I don't want to say too much more about applications since you're going to hear more. And in the deep learning track for the rest of the day, you'll hear all sorts of examples as well. So I just wanted to close with that. So come to my talk at the end of the day. Well, come to the whole session, the whole track, and I'll have kind of a wrap up with some more interesting examples. We also are offering an online course. So I encourage everybody who's interested in learning more. It's designed for people with no background in the field to kind of get a feel for what is deep learning. It's 5 units. It's available to anyone. It's free. The classes are live online. And then we have hands-on labs where we actually run the lab in the cloud. So you don't need a GPU. You can do all of the exercises just through basically a browser-based application that runs in the cloud. And then we're holding office hours. So NVIDIA's experts in deep learning will be available in the chat forums live to answer questions. So it's Wednesday from 9 a.m. to 10 a.m. Pacific time. I think we've had 2 or 3 of the classes so far. So it's about halfway through. Everything is recorded though, so if you've missed anything, you can just go back and watch the lectures. And then after you leave GTC, please continue to learn more about all this technology. So like I said, we have this free deep learning course. I encourage everyone who's interested to learn a little bit more about our GPU computing platform with CUDA. We've virtualized the classroom just like we virtualized the GPU. You can take all of our training online. You don't need a GPU. You can do the programming exercises, run everything in the cloud through this quick lab system. The introductory courses are free. If you'd like to take more courses, contact your NVIDIA representative. We'd be happy to share some free quick lab credits with you. And as Mark was saying earlier, we're very excited about Grid. Again, we virtualized the sales process. You don't need to buy any hardware to try it out. Just go to this website, nvidia.com/try-grid, and you can get free access to a demo setup, or you can try all kinds of applications online for free, and contact your NVIDIA representative to learn more. So with that, I'm going to wrap up. Thank you, everyone. Have a great rest of the day. Thanks for coming to GTC.
Thank you, Mr. Cohen and Mr. Hamilton for giving the wonderful speech.